The Avro Lancaster shuddered through flak-torn skies over the Ruhr Valley, its 7-man crew squinting into absolute blackness. Flight Lieutenant James Murray checked his watch. 02:47 hours. March 1941, and called back to his navigator. 2 minutes to target. The problem was simple and terrifying. Neither of them had any real idea where the target actually was. They were aiming for the corrupt steelworks in Essen, one of Nazi Germany's vital armament factories. What they would probably hit, if anything, was a cow pasture 3 miles to the south. This wasn't incompetence. It was the brutal reality of RAF Bomber Command's early war effort. The numbers told a story that would have sickened Churchill if he'd seen it. In August 1941, a civil servant named David Benson analyzed 4,000 Bu-65 reconnaissance photos from bomber raids. His report landed on desks like a grenade. Of all the aircraft recorded as attacking their targets, only 1 in 3 got within 5 miles of the aiming point. In conditions of searchlights and industrial haze, that figure collapsed to 1 in 10. We're not talking about missing a factory. We're talking about missing entire cities. Tactically, the solution was straightforward, but nearly impossible to execute. German industry had to be destroyed. But Germany had learned from the Blitz. Every major city went dark at night. No street lights, no factory lights, blackout curtains in every window. Bomber crews flew for hours over a landscape that looked like crossing the Atlantic at midnight. Just endless nothing. Navigation relied on dead reckoning, position calculated from airspeed, heading, and time. But winds at 15,000 FT rarely matched the forecast. A navigator might estimate a 30-knot headwind when the actual was 50. After 3 hours, that error could put you 15 miles off course. You'd arrive at your calculated position, see nothing, and drop your bombs on whatever you hoped was German and important. On paper, the doctrine made sense. Area bombing, hitting general industrial zones rather than precise points, should work when you couldn't see. But area still meant finding the right area. Crews identified themselves over target by spotting rivers, coastlines, or distinctive rail junctions using moonlight or the glow of earlier fires. Overcast nights, which were most nights over northern Europe, afforded nothing. Bomb aimers would seize any break in cloud, spot dark shapes that might be buildings, and release their loads, hoping for the best. The human cost of that guessing game was staggering. Bomber Command was losing aircraft at rates that would have depleted the force within months. A crew's statistical chance of surviving a 30 operation tour was roughly 44% in early 1942. They climbed into Lancasters and Halifaxes, knowing they were probably going to die, and their sacrifice wasn't even accomplishing the mission. German production barely flickered because most bombs landed in fields, forests, and farming villages. Something had to change, and fast. The Americans arrived preaching daylight precision bombing, which sounded promising until German fighters tore into B-17 formations. Night remained the only viable option, but night meant blindness. The RAF needed a way to see in the dark, and they needed navigators who could use whatever the boffins invented. What nobody yet realized was that the technology was coming, but it would take one man's mathematical heresy to make it work. The solution arrived in early 1943, mounted in the belly of a modified Halifax bomber, and it looked like something from a science fiction serial. H2S, so-called either for Home Sweet Home or because some engineer liked chemistry jokes, was a rotating radar scanner that painted the ground below on a cathode ray tube. For the first time in aviation history, a navigator could see through clouds and darkness. The device swept a radar beam in a full circle beneath the aircraft. Returns bounced back differently depending on what they hit. Water absorbed radar waves and showed up dark. Buildings and metal structures reflected strongly and glowed bright green on the scope. A trained operator could, in theory, identify cities, rivers, coastlines, even individual factory complexes. The technology itself was brilliant and revolutionary, representing some of the war's most advanced electronics work. At its heart was the magnetron, a cavity resonator that generated microwave frequencies, one of Britain's most closely guarded secrets. Churchill had personally approved its use in aircraft, despite fears that a crashed bomber might hand the technology to Germany. The Air Ministry banked everything on H-2S, believing it could transform bomber. Command from a blind force dropping ordnance into the void, into a precision instrument capable of systematically dismantling the German war machine. February 1943 marked its operational debut. Pathfinder Force, the elite squadrons that marked targets for the main bomber streams, received the first sets. These were the RAF's best crews, men selected for exceptional skill and steady nerves. If anyone could master the green glowing scope, they could. The initial raids against Hamburg showed promise. Navigators reported identifying the distinctive shape of the city and its industrial complexes on the screen. And for the first time, Bomber Command could aim with a semblance of certainty rather than blind faith. The Elbe River glowed faintly below, a sharp line separating the city from the water. Bombing accuracy had clearly improved, and the air staff began writing optimistic reports about the future of the strategic bombing campaign. What those reports didn't capture, however, was the crushing cognitive overload of actually using H-2S in combat. Imagine yourself in the navigator's seat, crouched in a cramped, freezing compartment, the aircraft jolting violently from turbulence and evasive turns. Flak bursts close enough to rattle your teeth. You're wearing an oxygen mask, heavy gloves, an electrically heated suit, and staring at a circular green screen 9 inches across, where shifting blobs of light supposedly represent the world below. The display wasn't a map. It was a constantly changing radar return. Every sweep, every adjustment of gain, every slight roll of the bomber altered the image. A navigator had to interpret the pattern, match it to charts, determine wind speed and direction, compute a heading correction, and relay it to the pilot, all while the bomber roared toward the target at 240 miles per hour. The mental strain was brutal. Men who'd been top of their navigation classes, many with mathematics degrees from Cambridge or Oxford, found themselves frozen by the information flood. The real difficulty came in the final bombing run. After an hour of plotting position with H-2S, you had to pinpoint the exact aiming mark and time the bomb release. That meant measuring the target's range and bearing on the scope, then calculating the release point with trigonometric tables and a Dalton computer, a circular slide rule every navigator carried. In theory, it took 90 seconds. In practice, with gloved fingers and flak exploding outside, it was nearly impossible to get right. Crews could now see their targets, which was revolutionary, but seeing and hitting were two very different challenges. The gulf between them was filled with mathematics no human could solve fast enough in combat. Group Captain Dudley Saward was never meant to be the man to fix this. A Cambridge-trained mathematician who'd wandered into operations instead of staying behind a research desk. He was serving in late 1943 as senior air staff officer at Bomber Command headquarters. His job was to analyze raid results by day and puzzle over their failures by night. The numbers gnawed at him. Pathfinder crews, bomber, Command's best, were still placing markers an average of 2 miles from their intended point using H-2S. 2 miles might sound acceptable until you remember these were the elite. The main bomber force added further errors on top, and factories continued to operate largely undisturbed. Somewhere between identifying the target on the radar and hitting it, something fundamental was breaking down. Saward began visiting operational squadrons, standing behind navigators on training flights to watch them work. What he saw made his mathematician's instincts recoil. The men were doing exactly what they'd been taught. They'd spot the target on the H-2S scope, measure its range and bearing, then reach for their Dalton computers. The device itself was ingenious, a circular slide rule for aerial navigation. You'd set airspeed, line-up heading, and read off solutions for drift, ground speed, and bombing angle. But during the critical minute before bomb release, navigators were fumbling with it, setting scales, reading values, cross-checking tables. Done carefully, the process took 2 to 4 minutes, during which the aircraft covered nearly 10 miles. So they rushed. They skipped steps, rounded figures, guessed under pressure. Saward once watched an Oxford-trained navigator make a simple arithmetic slip that threw the aim off by 3 degrees. At 10 miles, that meant a miss of almost a mile. This wasn't incompetence, it was human limitation. The breakthrough came during a violently turbulent training flight in November 1943. Saward watched yet another navigator struggle with the Dalton when something clicked in his mathematical intuition. Everyone had been framing the problem wrong. They treated it as trigonometry, measure 2 values, calculate the third. But it wasn't trigonometry at all. It was geometry. On the H2S scope, 3 reference points already existed: your aircraft at the center, the target's position on the screen, and your projected ground track. If you used those spatial relationships directly, you could bypass the entire chain of calculations and, for the first time, make radar bombing fast enough to be truly accurate. The line along which you were flying, your ground track, completed the triangle. Those 3 points made the problem visual rather than numerical. You didn't have to grind through calculations. The answer was there to see. The bombing angle was revealed directly on the scope. Saward grabbed a grease pencil and sketched the idea on scrap paper, instead of separately measuring range and bearing and then computing. What if navigators simply drew a line from the aircraft's position through the target return on the H2S scope, then measured the angle between that line and the aircraft's track? That angle was the bombing angle. No trigonometry, no Dalton computer, no tables, just direct visual measurement. The method violated every rule of formal navigation training. It was crude, inelegant, and from a traditional navigator's point of view, flagrantly improper. But Saward's mathematical intuition told him it would work, and crucially, it would work fast. A navigator could read that angle in 5 seconds instead of 2 minutes, and speed in the final bombing run was everything. Once you saw it, the geometry was almost insultingly simple, which may explain why nobody had spotted it earlier. Navigation school had drilled into every RAF navigator. Measure range and bearing, then calculate your solution. The proper mathematical procedure. Saward's shortcut threw that orthodoxy away and relied on raw visual judgment. Here's how it operated in practice. The H2S scope showed your aircraft at the center of the circular screen. Your ground tracker, the actual direction you were moving over the ground, appeared as a line through that center point. The target showed up as a bright return somewhere on the disk. Draw a straight line from the center to that return. The angle between this target line and your ground track line is the bombing angle, the direction you must allow for aircraft motion to hit the aim point. The conventional method measured range with the scope's range rings, measured bearing with the rotating cursor, and fed both numbers into the Dalton computer together with airspeed and altitude to derive the angle. Saward's method removed all those intermediate steps. You eyeballed the angle on the scope and called it to the bomb aimer. If the target was 30 degrees right of track, the bombing angle was 30 degrees. End of story. The math behind it is simply the geometry of angle measurement. Trigonometry calculates angles from ratios, sines, tangents, and so on. But angles also exist independently as geometric quantities you can measure directly with a protractor. Effectively, the H2S scope already functioned as a protractor. The bearing cursor, previously used only for target bearings, could just as well be read as an angle measuring device. Saward refined the idea into a practical tool, a transparent overlay, a clear plastic disc etched with radial lines at 5-degree intervals to be placed over the H2S scope. Rotate the overlay so one of its radial lines aligns with your ground track, then read which radial points at the target. The whole procedure took seconds. The technique delivered another major benefit Saward recognized immediately. It automatically compensated for wind. Traditional navigation forced you to calculate wind drift separately, then apply that correction to the bombing solution. Another layer of work and source of error. But the ground track line on the H2S scope already showed where you were actually traveling over the ground, wind effects included. Measuring the angle relative to that ground track, therefore inherently captured current wind conditions. There was a limitation. The method gave the required angle, not the precise release instant. Bomb aimers still had to compute release timing from altitude and airspeed, a simpler, routine calculation within their skill set. By offloading the complex trigonometry from the Navigator to a quick visual read, Saward decomposed one impossible task into two manageable ones. He tested the idea rigorously. On paper, eyeballing an angle with a 5-degree overlay should introduce errors of +2 3 degrees. That looks sloppy beside theoretically precise calculations carried out to decimal places. But Saward understood the operational truth. Theoretical precision means nothing if you cannot achieve it under combat conditions. A bombing angle estimated to +2 3 degrees in 5 seconds was vastly superior to an angle calculated to theoretical exactness in 3 minutes, especially when rushed calculations under fire typically produced errors of 5 degrees or more. The tactic was so simple that Saward at first doubted himself. Surely someone else had thought of it. But in practice, it worked. Surely the navigation experts at the training schools had once considered direct angle measurement. Yet they hadn't, because they were trapped inside the rigid framework of calculation-based navigation. To them, measuring by eye seemed unprofessional, imprecise, even beneath the dignity of a properly trained navigator. Saward was about to discover just how deep that institutional prejudice ran. When he first presented his geometric method to senior navigation officers at Bomber Command Headquarters in December 1943, the reaction wasn't mere skepticism. It was moral outrage. Wing Commander Peter Hargreaves, the command navigation officer, actually rose from the table and declared that the technique was not how gentlemen navigate. That single phrase captured the entire cultural problem Saward faced. To the RAF's navigation establishment, this wasn't about mathematics. It was about identity. Resistance came from several fronts, each with its own flavor. The oldest navigators, men who had trained in the 1930s by sextant and starsight, saw Saward's idea as an insult to their craft. Navigation to them was a discipline demanding intellect, precision, and patience. Any novice could eyeball an angle on a glowing screen. Where was the skill in that? These veterans had spent years mastering trigonometric tables, perfecting Dalton computer techniques, and learning to calculate wind drift by hand. Now a staff officer was telling them their expertise was obsolete. The instructors at training schools had another reason to resist. Their entire curriculum was built on calculation. Cadets spent months learning dead reckoning, celestial navigation, radio fixes, and finally H2S operation. All mathematical disciplines built on precision and computation. If Saward's visual method replaced all that, what became of the course? More importantly, what became of the instructor's authority? Their prestige came from mastering complexity. A technique that could be taught in an afternoon threatened to make them redundant. The opposition even took on a class tone. Many senior officers came from public school backgrounds, steeped in classical education. Euclidean proofs, logarithmic tables, mental arithmetic, the marks of an educated gentleman. Visual estimation reeked of tradecraft, the sort of thing done by mechanics and artisans, not officers. Squadron leader Edmund Morris even wrote a memo warning that adopting Saward's method would lower standards and attract the wrong kind of recruit to navigation training. The technical objections, when they appeared, were more polished but no less obstinate. Experts argued that visual angle measurement could never match the precision of calculated solutions. They produced elaborate statistical analyses showing that human estimation introduced intolerable error. Saward countered that combat stress created far worse errors in calculation, but the argument fell flat. The establishment compared his real-world method against a fantasy of mathematical accuracy that existed only in classrooms, not in bombers dodging flak over the Ruhr. Some critics, to be fair, were cautious rather than arrogant. Air Vice Marshal Donald Bennett, commander of the Pathfinder Force, feared the disruption of changing technique mid-campaign. His navigators were the best in bomber command, already experts with the current system. What if the new method worked inconsistently, brilliant for some, disastrous for others? Bennett had seen too many innovations fail between laboratory and combat. His skepticism came from scars, not pride. Still, bureaucracy moved with glacial slowness. Saward's proposal wound its way through committees, subcommittees, and review boards. At every stage, officers demanded revisions, new trials, and more data. The Air Ministry's Directorate of Navigation insisted on formal tests before authorizing operational use, which meant paperwork, testing protocols, and delays, all while Bomber Command kept losing aircraft and missing targets. What frustrated Saward most was the contradiction at the heart of it all. Everyone agreed bombing accuracy was abysmal. Everyone admitted navigators were overloaded. Yet when presented with a simple solution to both problems, the institution rejected it for lacking elegance. It was as if they preferred losing the war like gentlemen to winning it like mechanics. By March 1944, Saward had been arguing for 4 months with nothing to show. The establishment had buried his idea under layers of procedure and polite contempt. He had demonstrated it, flown it, written it up. None of it mattered. His method was deemed ungentlemanly, and that seemed to settle the matter. Then he realized what he needed wasn't more persuasion. It was proof that couldn't be dismissed. He needed results, and he found his chance in an unexpected place. 582 Squadron, a Pathfinder unit based at Little Staunton in Cambridgeshire, was struggling with an influx of new crews. The squadron had just received a batch of recently trained navigators in April 1944, men competent enough to pass their courses, but not yet at the elite Pathfinder level. Squadron leader David Clark, the navigation leader, was frustrated. His newcomers could use H2S for general positioning, but consistently failed during the final bombing runs. They'd locate the target area, then scatter their markers across a 2-mile radius, unable to work their Dalton computers fast enough under pressure. Clark had heard whispers of Saward's unorthodox method through the informal network of navigation officers. Unlike the stiff traditionalists, Clark was a pragmatist who'd flown 43 operational sorties and seen too many good men die from navigation errors. He didn't care about elegance or tradition, only results. When Saward approached him about an unofficial trial, Clark agreed immediately, with one condition: they would do it quietly, without alerting headquarters until they had results worth defending. The trial began on April 23, 1944, with 6 crews from 582 Squadron. Saward spent an afternoon teaching them his geometric shortcut using a training H2S scope in a classroom. He showed how to find the ground track, visualize the line from aircraft to target, and measure the angle with the bearing cursor. The navigators were skeptical. Their schooling had drilled into them that visual estimation was sloppy, unprofessional. But Saward had a persuasive argument. Try it once and see if it's faster. The first training flights were a revelation. Navigators who'd taken 3 minutes to compute bombing angles were now calling them out in 15 seconds. Flight Lieutenant Robert Hammond recorded in his logbook, "Felt like cheating. Found target on scope, eyeballed angle, called it to bomb aimer. We were lined up before I'd even have finished pulling out my Dalton." The speed advantage exceeded Saward's own predictions because he had underestimated how much stress slowed down calculation. Removing that cognitive burden was like lifting a weight off their minds. The question remained, what about accuracy? Clark designed a strict comparison, training runs against known ground targets with cameras recording every impact. 6 crews using the old calculation method, 6 using Saward's visual one. Identical weather, routes, and altitudes. The trials ran 2 weeks, 12 sorties per crew. Clark personally analyzed every frame, measuring distance from intended aim point to actual marker. The results were astonishing. Traditional method crews averaged 1,147 yards from the aim point, with high variance. Some runs were excellent, others wildly off, depending on how rushed the Navigator felt. Crews using Saward's method averaged just 312 yards from the aim point, with far tighter clustering. They weren't merely more accurate, they were more consistent. The simplicity of the visual method made it robust under stress. Fewer steps meant fewer chances for error. Clark documented every detail: weather, crew experience, target type, even navigators' emotional state before each flight. He wanted data so thorough that no skeptic could dismiss it. By mid-May, he had proof. Saward's approach improved bombing accuracy by roughly 600% for average crews. For weaker navigators, the improvement was even more dramatic. Men who'd missed by a mile were now placing markers within 400 yards. An unexpected benefit also emerged: reduced fatigue. Navigators using the visual method arrived at the target fresher, sharper, and made better decisions. Flight Lieutenant James Peterson noted in debriefing that he actually had mental bandwidth. Left to cross-check his work and watch for threats, impossible when buried in trigonometry. Clark compiled his findings into a 20-page report, complete with diagrams, statistical tables, and photographs. He handed it to Saward on May 28, 1944. The evidence was irrefutable. Saward's crude, ungentlemanly, theoretically inferior method outperformed the polished techniques taught across the RAF. Clark added his own recommendation: immediate adoption throughout the Pathfinder force. Now Saward had ammunition. This wasn't theory anymore, it was operational fact. The establishment could sneer at his lack of elegance, but not at film reels showing markers landing almost dead on. Clark's experiment gave him the one weapon bureaucracy couldn't withstand: results that saved lives and hit targets. The only question was whether that proof would be enough. Clark's report reached Air Vice Marshal Bennett's desk in early June 1944, just as Bomber Command was escalating operations in support of the Normandy invasion. Bennett remained wary. He'd seen too many revolutionary systems fail, but the timing favored Saward. Pathfinder squadrons were flying multiple sorties nightly, marking D-Day targets where accuracy was everything. Just operationally desirable, it was morally essential. These were no longer distant German industrial targets. They were tactical strikes near Allied troops and French civilians. A 2-mile error could mean bombing your own men. Bennett authorized a controlled operational test. 3 Pathfinder squadrons would adopt Saward's method for tactical targets in France, while 3 others continued with traditional navigation as a control. The trial ran for 30 days, beginning 10th of June 1944. Photo reconnaissance would assess every strike, and the results would decide whether the geometric method went service-wide or was quietly shelved. Bennett's authorization memo was blunt. "We will follow the evidence, regardless of how it reflects on current training methods." Operational results arrived faster than anyone expected, because the sortie tempo was relentless. Squadrons flew nightly, sometimes twice, striking German positions, rail junctions, and supply depots. Within 2 weeks, the pattern was unmistakable. The 3 squadrons using Saward's technique averaged marker placement just 247 yards from the aim point. The control group using traditional methods averaged 1,230 yards. The gap was so large, Bennett terminated the trial after 3 weeks. On 2 July 1944, he ordered immediate adoption across all Pathfinder squadrons. The navigation establishment made a last attempt to block the change. The Air Ministry's Director of Navigation insisted widespread adoption required full integration into the training syllabus, months of curriculum work. Saward answered with a radical counter-proposal: forget the schools. The technique was simple enough to teach squadron to squadron, navigator to navigator, issue a 2-page technical bulletin, and let crews teach themselves. Bennett backed the plan over vigorous objections from the training directorate. Technical Bulletin 74344 went out on 15th of July 1944. Remarkably concise, it ran only 847 words and included 3 diagrams showing the geometric principle, the angle measurement technique, and the transparent overlay design. Station workshops could fabricate overlays from acetate and a drafting compass. The bulletin's tone was almost apologetic, while the method appeared less rigorous than calculation-based techniques. Operational trials demonstrated significant gains in accuracy and speed under combat conditions. Adoption across Bomber Command followed swiftly. Once crews tried the method, navigators who'd struggled with H2S suddenly found confidence. Squadron commanders reported navigator washout rates. Men unable to cope with operational stress and reassigned fell by roughly 40% in August 1944. The technique raised the floor of navigator competence, converting marginal performers into capable operators. By September 1944, approximately 70% of H2S-equipped aircraft were using Saward's geometric method as their primary bombing procedure. The effect on the strategic campaign became evident in German production records. Post-war assessments showed bombing accuracy improved markedly over the late summer. Attacks that had previously damaged 30% of a target complex were now achieving 70–80% damage. German repair units could not keep pace. The technique proved especially valuable in the war's final months, when Bomber Command increasingly supported the ground advance. Tactical targets, rail yards, bridges, troop concentrations demanded a precision that older methods could not provide. Flight Lieutenant Richard Thompson of 35 Squadron recorded a mission on 15th of March 1945 in which his crew marked a German headquarters in a French town and placed their marker within 80 yards of the aim point. Main force bombers destroyed the headquarters while largely sparing nearby civilian buildings. Thompson wrote, "Did what we couldn't have done a year ago, actually hit what we aimed at without slaughtering friendlies." The statistical transformation was captured in Bomber Command's operational research, comparing Q1 1944 to Q1 1945. Circular error probable for Pathfinder markers fell from 1,140 yards to 287 yards. Saward's geometric method did not win the war by itself, but it was a significant factor in the elevated effectiveness of the bomber offensive in the conflict's final year. German industry, which had endured and even increased output through 1943 despite heavy raids, finally buckled in late 1944 as bombs began striking factories instead of farmland. The human cost side mattered just as much. More accurate bombing meant fewer sorties were required to achieve objectives, and fewer sorties meant fewer crews lost. Bomber Command's casualty rates dropped in the last year of the war for multiple reasons, but improved navigation was among them. Crews spent less time fumbling over targets with slide rules and more time egressing to safety, reducing exposure to flak and fighters. The method once condemned as ungentlemanly thus ended up saving the lives of the very gentlemen who had scorned it. The war ended in May 1945, and Dudley Saward expected his geometric method to fade like many wartime improvisations. Bomber Command was demobilizing quickly, and the peacetime RAF seemed likely to revert to pre-war standards that prized traditional navigation training. He was wrong. The method endured because it had altered how navigators conceived their role in the kill chain. Post-war analysis revealed an unexpected consequence. Saward's technique didn't merely boost bombing accuracy, it reshaped crew dynamics. Under calculation-based navigation, the navigator sat isolated in his compartment doing complex mathematics, while the rest of the crew waited for solutions. The geometric method changed that. Navigation became collaborative. Bomb aimers could verify the navigator's angle calls. Pilots learned the geometry well enough to suggest corrections. Even wireless operators picked up the basics. The simplicity that once seemed unprofessional actually made the entire crew more effective. The RAF's post-war navigation training command faced an institutional crisis. The service had spent the war teaching calculation-heavy methods, while operational squadrons had adopted a visual technique that contradicted the syllabus. The training establishment had two choices: admit their doctrine was obsolete or incorporate the geometric approach into the professional framework. They chose the latter, which demanded remarkable intellectual flexibility from men who had opposed Saward's idea so fiercely. Wing Commander Hargreaves, the same officer who had called the method ungentlemanly in 1943, authored the 1947 Revised Navigation manual that made geometric angle measurement the primary technique for radar bombing. He changed his mind after seeing the operational data and, to his credit, acknowledged it in the manual's introduction. Wartime experience showed that simplicity under operational stress often outweighed theoretical precision in peacetime conditions. The modern navigator, the manual argued, must master both calculation and visual estimation. It was as close to an apology as the RAF would issue. Saward's influence crossed the Atlantic. American crews, operating H-2X and AN/APQ-13 radar, faced similar targeting problems. When U.S. strategic air forces reviewed British practice in late 1944, they quickly adopted Saward's geometric method. It spread to B-29 crews in the Pacific, proving effective over featureless ocean as well as over European industry. A technique born to find German factories ended up guiding bombers over Japanese cities. Post-war avionics development absorbed the lesson in unexpected ways. Early analog bombing computers of the late 1940s were designed around geometric principles rather than purely trigonometric routines. Successors to the Norden bomb sight used visual angle inputs as core data. Saward's wartime improvisation became the theoretical underpinning for automated targeting and navigation systems. The deeper legacy was cultural. Before Saward, military innovation typically flowed from research establishments and training schools to the front line. His success proved that field experience could produce insights the theorists missed. The RAF established formal channels, allowing operational crews to propose procedural changes without first securing academic validation. This institutional shift accelerated post-war aviation development. Modern avionics still reflect Saward's central insight. Human operators perform better with intuitive visual interfaces than with calculation-heavy procedures. Head-up displays present geometric targeting information, angles, vectors, intercept cues, directly to pilots rather than forcing mental computation. The F-35's helmet-mounted display, which overlays targeting angles on the pilot's view, traces conceptual lineage to Saward's transparent overlay on an H-2S scope. The story also taught militaries about institutional resistance to innovation. Post-war RAF reforms included procedures for rapid field testing of promising techniques without waiting for training school sign-off. That reform saved years when integrating technologies such as precision-guided munitions and digital navigation systems. Saward himself received little public recognition. He was appointed OBE in the 1945 Honours List, respectable but not spectacular, buried among thousands of awards. His contribution wasn't a flashy invention or a daring raid. It was simply a better way to measure an angle. He returned to civilian life as an engineer and rarely spoke of his wartime role. When aviation historians interviewed him in the 1970s, he seemed genuinely surprised anyone still cared about his geometric method 40 years on. Navigators, however, remembered. The post-war RAF Navigators Association adopted the transparent angle overlay as part of its insignia. Graduates of post-war navigation courses learned Saward's technique as foundational. When the last H-2S-equipped bombers were retired in the 1960s and replaced by aircraft with automated systems, veteran navigators kept their acetate overlays as mementos. Those small pieces of plastic symbolize something important, proof that the best solution isn't always the most sophisticated, and that mathematical elegance matters less than practical effectiveness. When lives are on the line, the once forbidden math trick had become standard procedure, and in so doing it showed how war can create space for ideas peacetime institutions would otherwise reject.